This is EE300, Fall 2016, Module 1, Video 6, using the Laplace transform to solve differential equations. In this video, we'll use a Laplace transform to find circuit responses for circuits that are described by differential equations. We'll look at the parallel RL circuit in the case of a step input and an exponential input. We'll then take a brief review of what we did here. Solving circuits using Laplace. To use the Laplace transform to find circuit outputs for circuits described by differential equations, we use a three-step process. First, we develop the differential equation or set of differential equations governing circuit dynamics. Second, we then transform that equation or those equations into the Laplace frequency domain and solve for the branch variable or variables of interest as functions of S. Finally, we then apply the inverse Laplace transform to those S-domain functions to find the desired time domain waveforms. Consider the parallel RL circuit driven by a current source of strength I sub S of t. Let's find the differential equation relating the inductor current I sub L to the current source waveform. Since this is a parallel circuit, it seems natural to use KCL to sum currents as a way of finding the differential equation. Summing the currents at the top node, we have minus the source current plus the current leaving through the resistor plus the indicated inductor current should all sum to 0. By the device characteristic for the inductor voltage is L times the derivative of the inductor current. By replacing V sub L with L d sub IL dt in the expression for the resistor current, we get our differential equation. We write it in a standard way with the output variables and the derivatives on the left and with input variables and their derivatives on the right. Note that we left things in terms of literals. This will make it easier to perform checks looking for dimensional consistency. From previously having analyzed circuits using time domain techniques, we know that L over R has the units of time, so all three terms in the differential equation have units of current. RL circuit with step input. Suppose our circuit components have the given values. The resistance is 2 k ohms and the inductance is 1 henry. The input current, as shown on the graph, is 0 for times t less than 0 and is 10 milliamps for t greater than or equal to 0. We can write the current over all times t in terms of the unit step function as 10 u of t milliamps. Our goal is to find the inductor current for all times t. For t less than 0, the input current is 0. This means that any energy that may have been stored in the inductor a long time ago has long since dissipated. From this kind of physical reasoning and knowledge about how circuits act under special conditions, we state that the inductor current is 0 for t less than 0. We could have used our knowledge of differential equations to argue that 0 is the particular solution that accompanies the particular input 0. Again, we would have to argue that any natural solution for t less than 0 has decayed to 0 for any finite times. Because the inductor current is continuous even if the voltage were to change discontinuously, the inductor current at t equals 0 has to be the same as it was right before t equals 0. This follows from the integral form of the device characteristic for the inductor. We're integrating over an infinitesimal time from 0 minus to 0 itself, so the current can't change. Now we want to apply the Laplace transform to the differential equation. Because the Laplace transform is a linear operator, we can apply it to each term individually. The Laplace transform of the derivative of the inductor current is S times cap I sub L of S less the value of IL of t at t equals 0. The transform of IL of t is just cap I sub L of S. The transform of the source current is cap I sub S of S. We can factor the coefficients out of cap I sub L of S and take the scaled initial condition term to the other side, and then divide both input and initial condition terms by SL over R plus 1 to solve for cap I sub L of S. Since the Laplace transform is an integral over time, the Laplace transform of the input current and the inductor current will both have the units of current times time. L over R has dimensions of time, and the Laplace frequency variable S has dimensions of per time, so S times L over R is dimensionless. Both sides of our equation have the units of current times time. Now we use the component and initial condition values. We know we're going to want the denominator to have a leading coefficient of 1, so we multiply everything by R over L over R over L. For R equals 2 k ohms and L equals 1 henry, R over L is 2,000 per second, which is 2 per millisecond. From our earlier analysis, I sub L at t equals 0 is 0. We plug these into our expression for cap I sub L of s, and the initial condition term drops out, leaving us with cap I sub L of s equals 2000 over s plus 2000 times the Laplace transform of the input. Now we take the input waveform into the Laplace domain. The Laplace transform of the constant 10 milliamps is 10 over s milliamp seconds. It's not necessarily to write the units here, even though you should be aware of what they are. We plug that value into the expression for the Laplace transform of the inductor current and write it without simplifying, but arranging terms in the denominator and numerator for convenience. We could have written the numerator as 20,000, and we could have written the denominator as s squared plus 2000s, but as you'll see, that would only increase the likelihood of making a mistake when we inverse transform. To inverse transform, we do our usual partial fractions by cover-up. We write cap I sub L of s as something over s plus something over 2000, s plus 2000. We cover up s and let s equal 0 in what remains to find that the weight of 1 over s is 10. We cover up s plus 2000 and let s equal minus 2000 in what remains to find that the weight of 1 over s plus 2000 is minus 10. A quick check confirms that were we to put everything over a common denominator, the coefficient of s in the numerator would vanish as it should. We inverse transform term by term to find that the inductor current is 10 less 10 times e to the minus 2000t milliamps for t greater than or equal to 0. We can put that expression for I sub L when t is greater than or equal to 0 with the value of 0 for t less than 0. Since multiplying by u of t makes everything 0 for negative times, we can write one expression, I sub L of t equals 10 times 1 minus e to the minus 2000t u of t milliamps for all times t. The graphs show the input I sub s of t in red and the output I sub L of t in blue. Even though the graph doesn't show it, the forced response would be a constant 10 milliamps for t greater than or equal to 0, and the natural response would be minus 10 e to the minus 2000t milliamps, giving us the resulting total response. RL circuit exponential input. Let's analyze the same circuit with the same component values, but this time letting the source current be constant at 1 milliamp for t less than 0, and then exponential with an amplitude of 2 milliamps at a rate of 1,000 per second. Again, we want to find the inductor current over all time. Now, instead of our input having been 0 for a long time, it's been constant. We know that under constant conditions, an inductor acts like a short circuit. If the inductor acts like a short, its voltage is 0, so there's no voltage across the resistor and no current through the resistor. This means that all the constant current is going through the inductor, so for t less than 0, the inductor current is 1 milliamp. As before, continuity of the inductor current means that the current at t equals 0 is the same as the current just before t equals 0. That is, I sub L of 0 has to be 1 milliamp. Previously, we found that the S-domain expression for the transform of the inductor current was cap I sub L of s equals 2000 over s plus 2000 times cap I sub s of s plus 1 over s plus 2000 I sub L of 0. The Laplace transform of the input 2 e to the minus 1000t is 2 over s plus 1000. Who knows why there's a b there. With units of milliamp seconds. The initial condition is I sub L of 0 equals 1 milliamp. Plugging the S-domain expression for the input and the initial condition into our expression for the Laplace transform of the output, we write the left-hand term as 2 times 2000 over s plus 1000 times s plus 2000, and bring the right-hand term along. We write the left-hand term in terms of partial fractions as something over s plus 1000 plus something over s plus 2000. Covering up s plus 1000 and letting s equals minus 1000, we find 4 is the weight of 1 over s plus 1000. Covering up s plus 2000 and letting s equals minus 2000, we find minus 4 is the weight of 1 over s plus 2000. We inverse transform term by term to find I sub L of t is 4 times e to the minus 1000t minus 4 times e to the minus 2000t plus e to the minus 2000t for t greater than or equal to 0, which simplifies to 4 e to the minus 1000t minus 3 e to the minus 2000t. The current is in milliamps. We put this together with the result for t less than 0. The result has to be expressed piecewise using the two different cases of t less than 0 and t greater than or equal to 0. The graph shows the input current in red and the inductor current in blue. It also shows the forced response 4e to the minus 1000t and the natural response minus 3e to the minus 2000t for t greater than or equal to 0. In this video, we applied the Laplace transform to solve circuits described by differential equations. To do this, we had to derive the differential equation for the circuit. We used circuit knowledge and physical insights to find the response of the circuit for t less than 0. For t greater than or equal to 0, we applied the Laplace transform to the differential equation and then solved for the output in the Laplace frequency domain. We transformed the input for t greater than or equal to 0 into the S domain and put that and any initial condition values into our S domain expression. Then inverse transform to get the time domain output for t greater than or equal to 0. We could then put the answers for t less than 0 and t greater than or equal to 0 together to see the total solution over all time for the given input. This has been EE300 Fall 2016 Module 1 Video 6 using the Laplace transform to solve differential equations.